Morning, guys. Okay, so we missed our class on Tuesday, so this is from last Friday. So we'll have a quick look at the homework. It was to write up the experiment for how temperature affects rate of reaction. I pretty much had it done for you here. So this was surface area. This was the first one. And then down here, I called it an extension experiment because we were using the same experiment. We were using the production of carbon dioxide. But this time, instead of breaking up the calcium carbonate, we're going to leave the calcium carbonate alone, and we were going to change the temperature of the hydrochloric acid and see what effect that had. So you had your 30-second time frame and how much gas can you collect in 30 seconds. Okay, so that was essentially what we've done so far, okay? We were looking at factors affecting rate of reaction. The first one we looked at was surface area, and then the second one we looked at was temperature. So I just want to show you this, this one. So don't worry about this. So this one here, it's a kind of nice little demonstration of how temperature affects the particle collisions. Okay, so just watch. Okay, so on the left hand side here, the blue side, we have the low temperature particles, and on the right hand side we have the high temperature particles. So I suppose I want you to look at, remember that the reason temperature affects rate of reaction is because it gives the particles kinetic energy, so they move faster. So when they move faster, their collisions become more effective. Okay, so I want you to first of all look at the speed that the red particles are moving at, and then secondly, I want you to look at the number of effective collisions. Okay. Okay, so can you see the difference here? Look how much faster those red particles are moving than the blue ones. And as a result, almost all of their collisions are effective. So you're getting this massive number of effective collisions up in the 140s, while over here, the number of effective collisions was only 43. Now, that doesn't mean there was only 43 collisions. It means that in some of those collisions, the particles didn't have enough energy to react. Okay, so that, I just thought it was a nice little demonstration of how temperature affects rate of reaction. So the reason it affects it is because it gives the particles energy, and the more energy they have when they do collide, they're more likely to have an effective collision and actually react. So that's the first two factors affecting rate of reaction: surface area and temperature. We're going to do essentially one experiment when we get back to school to prove both of those. So we're going to produce carbon dioxide. I'll probably have it so that 3 groups are going to produce carbon dioxide, and they're going to be changing the surface area of calcium carbonate. So they'll be breaking the calcium carbonate up into smaller and smaller pieces and attempting the experiment again. And then the other half will be using temperature. So they'll be changing the temperature of the hydrochloric acid and seeing how that affects rate of reaction. Okay, but everybody will be doing ultimately the same experiment. Okay, so today we're going to move on to the third one. Hang on now, just let me get this on my iPad. So we're going to move on to the third one there. So the third factor affecting rate of reaction is concentration. I don't know why I don't have a 3 on it there. Okay. So number 3, concentration. Okay, so I'll come back to the experiment here, and I have another little demonstration to show you. But as you increase the concentration of the reactant, you increase the number of particles in a given volume. Okay, so increasing the concentration is like packing out the room. So it would be like Right, let's say we're in school, okay, and I ask somebody to go to Anya's office, okay, and I ask you to do that during class time when the corridors are empty. So there's no reason for there to be any collisions there. You could probably move quite quickly through the corridors and you wouldn't encounter any problems. Now, if I asked you to do the same thing right when the bell goes, right when everybody comes out of the staff room, Mr. Kennedy's room, the TY room, so people are pouring out into the corridors, and I'm asking you to leave the lab and head over to Anya's office. Much more likely that you will encounter collisions on that journey because there's way more people packed into the space. Okay, that's concentration. So an incredibly concentrated solution would be one where there's a huge amount of particles in a small volume, like there is in here. Okay, so both of these have the same volume, but there's way more particles. Way more particles packed in on the right hand side there than there are on the left. As a result, when those particles try to move, they're going to collide a lot more than in the diagram on the left hand side. And as a result, that affects how quickly the reaction happens. Okay, so let me show you. Not this one. I don't know actually, how do they? Yeah, so at a higher concentration, there are more particles in the same amount of space. So here we have, again, exactly the same thing. Same amount of space in both squares, but the one on the right has way more particles in it. This means that the particles are more likely to collide and therefore more likely to react. Okay, and here we have another little demonstration. Okay, so this time the right hand side, so you've got two boxes, same volume, so same amount of space, but there's more particles packed in on the red side than there are on the blue side. So when I start this, because there's less space in the red box, there should be more collisions. And that's how concentration affects collisions. Okay, notice here, because these are both at the same temperature, that the particles are moving more or less with the same kinetic energy. Because there are more particles in the red one and they're bouncing off each other, they're obviously picking up energy from those type of collisions. So some of them are kind of flying off a little bit faster, but generally speaking, they have the same amount of kinetic energy, but because they're more tightly packed, there's more collisions. Okay? So you need to get that idea across in the notes when you're taking your notes down. As you increase the concentration of the reactants, you increase the number of particles in a given volume. As there are more particles in concentrated solutions, there are more collisions. Okay, and generally speaking, provided there are effective collisions, more collisions mean an increased rate of reaction. Okay, the more collisions you have, the quicker the reactants are going to turn into products. So the quicker the reaction is going to happen. Okay, so this will be yet another experiment, which means you need to write up yet another experiment. Okay, so this experiment is different. We're not going to use carbon dioxide or production of carbon dioxide here. So the experiment we're trying to do overall is to investigate how concentration affects rate of reaction, and specifically the experiment we're doing is we're going to investigate if changing the concentration of sodium thiosulfate affects the rate of production of sulfur gas. Okay, so like normally I've left out the apparatus. I'm going to show you sort of what this experiment looks like in a minute, so you'll be able to draw the diagram. Okay. So what we do is we mix 50 ml of sodium thiosulfate with 50 ml of hydrochloric acid. Now, the picture I show you, they don't use a conical flask, but we're going to use a conical flask. You know, the one, no, sorry. So a conical flask, a conical flask is this one. Yeah. So you're going to have your 50 mils of sodium thiosulfate in here. You're going to add in 50 mils of your hydrochloric acid, and then they turn into, that turns into sulfur, okay? So sulfur is like a yellowy color, doesn't smell great either. So what we're going to do here, and I'll show you the other one, is that you're going to put a piece of paper down on the desk. On that piece of paper, you're going to put like a big black or red X, like use marker for a black or a red X. And you're going to put the conical flask on top of the X, okay? So you'll be able to look through the sodium thiosulfate and see the X. But when you put the hydrochloric acid in, when they mix together and turn into sulfur, it becomes a yellowy sort of orangey colour, and it blocks out the X, okay? And that's how we're going to do. Look at step 2 there. Once the reactants are mixed together, start the timer. Stop the timer when the X on the piece of paper under the conical flask is no longer visible, okay? So I'm just going to show you this. Like I said, they don't use a conical flask. I saw this somewhere. Okay, I think if I search sodium, it comes up. Yeah. Okay. So watch this, okay? So the reaction between sodium thiosulfate and hydrochloric acid can be used to investigate the effect of temperature on rate of reaction. Now, we're not using it to do temperature, we're using it to do concentration. That's not the point. I just want to show you how it actually works, okay? So here's the piece of paper, and they're putting the X on the piece of paper. We're then going to use a conical flask. The sodium thiosulfate's already in it. There goes the hydrochloric acid. Timer starts. Look at the colour change, okay? But you want to wait until the X has completely, there it is, disappeared. Okay, you want to wait until the X has totally disappeared. Right, so we're not going to use it in this way. Okay, let's watch that one more time. So once the hydrochloric acid goes in, so there's the hydrochloric acid going in. Once it goes in, start the timer. You will immediately start to see a colour change, but you're waiting until the X has completely disappeared from view around there, and then you record the time. Okay? So that's what it looks like. That's what we're going for here. So the sodium thiosulfate, when you place it down on top of the X, you can see through it. You need your timer ready. So one person will add the hydrochloric acid, the other person will start the timer. And then you're not just looking for it to change colour, you're really waiting for it to obscure that X. Okay? Now, because we're going to use this to do concentration, we're going to reduce the concentration of the sodium thiosulfate, okay? So in this first go, we put 50 ml of sodium thiosulfate into the conical flask. When you do it the second time, you're going to put 40 ml of the sodium thiosulfate and 10 ml of water. Okay, so what you're doing is you're diluting it. So it's still 50 ml that's going in, but only 40 ml of it is actually sodium thiosulfate. Okay, so you're still putting in 50 ml, but only 40 ml of it is actually sodium thiosulfate. And that means we have an 80% concentration. So the first round, you've got 100% concentration. All of what you put into the conical flask is sodium thiosulfate. But then when you do it the second time, you're going to dilute it slightly, 40-10. So now you've got an 80% concentration. Exact same experiment. So the hydrochloric acid doesn't get concentrated. That's 50 mils or it doesn't get diluted. So that's 50 mils all the time. So you put in your diluted sodium thiosulfate, you add in your 50 mils of hydrochloric acid, start your timer and wait for the X to disappear. And essentially, you're going to keep going until you get right down to a 20% concentration. So I have the concentrations done here in the results table. So the first time round, so you always use 50 mils of hydrochloric acid. That's not going to change. The sodium thiosulfate, initially it is a full 50 mils, which means it's 100% concentrated. Next round, you're going to do 40-10, so now it's 80% concentrated. Then you do 30-20, so now it's down to 60, and so on. Okay? And every time you're recording the time for the X to disappear. Okay? So I'd be interested, actually, it'd be nice when you're writing these up if you did put in your conclusion sort of like a prediction. Like, what do you think is going to happen? So based on obviously the conversation we're having here, in the first go, the sodium thiosulfate is at its max concentration. So there's loads of particles in that 50 mils. So does that mean that the reaction is going to happen quickly or the reaction is going to happen slowly? And then what happens when you make it more and more sparse? So as you move down that table, there's less and less particles in that sodium thiosulfate. So what is that going to do? So a prediction would be lovely. Okay, so I want you to write that up. Fill in the apparatus, fill in the diagram, draw the table, fill it in. Obviously leave this blank, we'll do that. The graph, write the word graph, write my writing, and then leave about half a page to draw a graph. And with the conclusion, again, you can write it, you can write the questions and just leave space for answers. Okay, so for the conclusion, you should be able to write, in this experiment, we aim to prove that the concentration of sodium thiosulfate had an effect on rate of reaction. Then I would write, what is your prediction? And answer that question, because that's a prediction, so that's meant to be done before. Then you write, did varying the concentration have an effect on the rate of reaction? Now, we're not going to answer that right now, so leave 2 lines. And then write, what evidence did you gather to support this outcome? And leave 2 lines. Okay? And then the last thing here is wear the precautions. Wear safety glasses to protect your eyes when working with hydrochloric acid and avoid skin contact with any of the chemicals. Okay? So that one needs... Why do I keep saying gas? Sorry. So that one needs to be written up, please. And then we've just got one more to do. And then we're finished with this chapter. All right. Thanks, guys. Bye-bye.